Hello and welcome. I'm Ken Ross from Columbia University, and I'm going to give the keynote talk for SIGMOD 2021 titled Utilizing and Designing Modern Hardware for Data-Intensive Computations, the Role of Abstraction. So what is a data-intensive computation? I use that word in the title. It could be a complex relational query. It could be some kind of loop in a conventional programming language over some large collection of data, perhaps stored as an array. You might imagine a data visualization application, some kind of linear algebra computation, or even a machine learning task using this type of analysis. So what is an abstraction? I use the word abstraction in the title. There are several meanings to abstraction, all of which I think say something relevant to today's talk. The first is a design principle, the idea that you encapsulate a particular method so that you expose a certain interface and hide all of the details at a finer level of granularity, allowing you to focus on one particular level and simplify your design task. An abstraction like a type system allows you to prevent errors by stopping you from misusing data of the wrong data type. So it's a kind of guiding principle that allows you to write correct software. Another use of the word abstraction would be just to simply distill interesting patterns from the data. So noticing, for example, that random IOs are more expensive than sequential IOs. Using that pattern, you would perhaps design your database management system to minimize random IOs. And a fourth use of the term abstraction is, for example, to figure out what's important. If you identify pieces of code that are shared between different modules in the system, pulling it out and deduplicating your code might be an important abstract task. Also, identifying chunks of code that get executed a lot and are therefore worth optimizing is another form of abstraction. So just to give you a high-level overview of what I'm going to talk about today, I'm going to talk at several different abstraction levels: the language level, the system level, the operator level, and a fragment level, which is really just a single line of code in some cases, in the context of both software and hardware. So hopefully, where I've indicated a check mark in this box, I'll have given you some examples of where some interesting things are going on in terms of understanding how modern hardware influences performance and how abstraction can help us understand the principles involved. So modern hardware was a term that I used in the title. What exactly does that mean? Well, obviously modern is a word that has a meaning that changes over time. What is modern today won't be modern tomorrow. Some of the things that are considered new 20 years ago are probably thought of as almost ancient today. So we're going to have to perhaps have a relativistic sense of what it means to be modern. In order to inform this process, I thought I'd start with a quick survey, a very bird's eye view of the field of modern hardware over the last, say, 5 decades of research. In the 1970s, performance for database management systems was very much dominated by the performance of a magnetic disk. And seeks and rotations are very expensive, and so you designed your algorithms and data structures to minimize IOs, and particularly to minimize random IOs. In the 1980s, people started thinking about how to design database machines. Could you design a machine that was specifically tailored for database workloads? People, in fact, tried to do this and succeeded to some degree at improving the performance. However, they found that the modest gains that they got with a particular technology became outweighed by Moore's law operating on general purpose processors. So even though there were limited successes, over time, Moore's law kind of swamped those gains. And so it was simpler just to stick with a general purpose processor and write database software in that context. In the 1990s, people started realizing that many applications could fit entirely in RAM, or at least the working sets of their data could fit in RAM. Since they weren't any more dominated by I/O performance, the next level of the memory hierarchy became the bottleneck, getting data to and from the RAM. So if you had a cache miss, your data was not in one of the CPU caches, that was the most important aspect of the performance, and finding algorithms that performed well in the cache became a higher priority. In the 2000s, people saw that other features of modern CPUs also played a role. And I've listed a few here. One is branch misprediction, where processors have a pipeline, and as they bring in instructions, they have to have a sense of which way a branch is going to go in order to keep the pipeline full. They can predict which way it's going to go, and if they're right, the processor can run at full capacity, but if they're wrong, there's a flushing of the pipeline and a stall. And in some database workloads where branches can happen with a 50% frequency, you may have a 50% misprediction penalty, and as a result, you will have much slower performance. Other features of modern machines that play a role in performance, people started using SIMD instructions, single instruction, multiple data. They started using multi-core machines that were becoming more and more available as the transistor counts kept going up, but the frequency stayed the same. More and more chips had multiple cores, and so getting parallelism without contention was a challenge. And many of these machines also had a feature called NUMA, which is non-uniform memory access. It took longer to access some regions of memory than others. Moving to the 2010s, people started thinking that the processor that's used to execute these data-intensive computations is itself something that was up for grabs. Maybe one could use some kind of unconventional CPU. An example here is the Xeon Phi, which is a less powerful processor than a conventional Intel processor, but because it's less powerful, you can have many more on a particular chip. And this processor used SIMD very extensively and multi-threading to get a different kind of performance profile than a conventional CPU. So maybe that is a platform that could be examined for data-intensive computations. GPUs were also considered as another form of platform that could be used for data-intensive computations, given the extensive parallelism and also the rapid improvement in GPU performance as GPUs were starting to ride a wave for graphics performance and later on for machine learning workloads. And finally, people also looked at database-specific accelerators. How would you design a processor yourself if you had to handle database workloads for large query processing tasks? So that was the bird's eye view of how the field may have progressed. I'm going to dive into a handful of selected contributions from my research group to identify a few key ideas and retrospectively identify abstractions from those ideas that hopefully will give some insight as to how the research contributes to making queries efficient. I'm going to start by talking about cache-sensitive B+ trees from 99 to 2000. By the way, I'm going to just put the titles and the years up here. At the end, I'll put a link to my homepage where you can find a list of publications and can look up the papers that correspond to these topics. So a conventional B plus tree has a node of size equal to a disk block. And this makes sense because that's the unit of transfer of data from the magnetic disk to the CPU. In RAM, if you have a RAM resident data set and you want to index it by a B plus tree, maybe you should do the same thing. What's the unit of transfer of data from the RAM to the CPU? Well, it's a cache line. So maybe a node should be a cache line. Well, that's a good idea. That seems to be the right unit. If you want to make the most of each cache line as it comes out, make use of the whole node. But the fan out of a cache line isn't as high as we would like. If you look at a B plus tree node, you can see that you have, in this particular example, 8 pointers and 7 keys fitting in a cache line. So if we imagine these keys and pointers are each 4 bytes big, they can fit into 64 bytes. And so our fan out, which is just the number of pointers, is only 8. One cache line gives us a branching factor of 8. And this is something that maybe we can improve on. So how do we improve on it? Well, we modify this abstraction. We're going to require that sibling nodes be contiguous in memory. This is not part of the original B plus tree definition. In the original B plus tree, every node could be placed arbitrarily in memory. When we do this, only one base pointer is needed for the set of children, and we can determine which node among the children we need to go to by calculating an offset from the base position. So here is what that might look like. We now have 15 keys in this cache line instead of 7, and one base pointer that points to a bunch of children that are stored contiguously in RAM. Because we have 15 keys, we now have a branching factor of 16, which is much better than our branching factor of 8 that we had originally. The higher fan out leads to shallower trees and fewer cache misses. And so this is a key insight that will improve performance when cache misses are the bottleneck, which is likely to be the case for many large RAM resident data sets. The next topic I'd like to discuss is selection conditions in RAM. So here is a code fragment that is trying to iterate through a bunch of records and check conditions on those records. If all of the conditions are satisfied, then an answer array will include the ID of the matching record. So what we can see here is that this for statement is iterating through all of the records. And inside the for loop, we have an if statement that's checking functions f1 up through fk on columns r1 through rk of record number I. I is the loop variable here. So if condition f1 is true and condition f true is true and so on up to fk, then we're going to add the index I to the answer set and increment j, which is the index into the answer array. So how do we try to optimize this in database management systems? Well, firstly, let's assume that we can, in fact, do this reordering safely, that there are no side effects in these Fs that would require a particular order of the F. So let's assume that these Fs are simple conditions that are just testing, x greater than 3 or something like that, so that we don't have any problems about reordering. So there was some earlier work that suggested that we order predicates by the cost of the function divided by 1 minus selectivity. Some early work by Joe Hellerstein suggested that that was the way to go, particularly in the context of expensive functions in object-oriented databases. However, that work didn't take into account the fact that there's quite a high branch misprediction penalty. And this penalty is very high when the selectivity is close to 0.5. And so this simple heuristic is not going to work when we have branch misprediction penalties of this kind. In this version of the code, I've made one small change, replacing the double ampersands with single ampersands. The double ampersand only checks the right-hand argument if the left-hand argument passes the test, whereas a single ampersand will evaluate all of the arguments and just do a Boolean AND on the result. So that means you potentially do more work because you have to do all of the arguments, all of the F function tests, rather than some of the time getting away with just stopping early if one of the early Fs fails. However, the assembly language generated from the first version would have K branch instructions, depending on checking the first condition, then the second condition, then the third condition, and so on. This version will only have one branch, where you take the combined function, and based on whether that's true or false, you'll have a branch. So one branch is better than K branches in terms of the potential for branch misprediction problems. On the other hand, you have to do more work. You have to test all of these functions instead of sometimes getting away with executing fewer. Nevertheless, because this could be better some of the time, it's worth keeping plans like this around. So it's more work for testing conditions, but sometimes that pays off. So let's try to push this a little bit further even. Can we execute the loop with no branches at all? At first, that seems a little bit counterintuitive. How could you do a test without a branch? Well, that reminds me of the Apollo 13 movie. Apollo 13 had an accident and they were rapidly building up carbon dioxide, and the people on the ground supporting the astronauts had to figure out a solution to their carbon dioxide problem. And the line from the movie that corresponds to this image that I have here is that we've got to make this fit into the hole for this using only this. So they had to make do with the equipment that they had in order to solve a problem that wasn't part of the original design specification. So think of this now as a database problem. Houston, we have a problem. Our if statements are no longer working. Roger that. Stand by for a solution. Okay, now if you're watching this video either before the conference or after the conference, I suggest you pause for a minute and see if you can figure out a way to execute this simple loop that I've just described without any if statements at all. If you're watching the conference, then please don't pause the video, because then you'll be late for the question time at the end. Okay, so I'm giving you an opportunity to pause. I'm now going to move to the solution. So here is a version of the code that uses no branches at all. So what we do is that we always write I to the answer array, but we only increment the index in the answer array if the test of all these Booleans is true. Now we can take advantage of the fact that in languages like C, true is represented as the integer 1 and false is represented as the integer 0. So in the situation where all these conditions are true, the result of this single ampersand expression, f1 and ... and fk, will be 1 if the conditions are all true, and 0 if at least one is false. So we will only increment the answer index, j, if all of the conditions are true. That means on the next iteration, we will either overwrite the previous value if the conditions had been false, or we'll write a new value if the previous conditions had been true. So this actually breaks a type abstraction. So that's one kind of abstraction that perhaps is problematic. Maybe this is an abstraction we want to break. On the other hand, there's a different kind of abstraction that kind of falls out of this. What we've done is change what had been a control dependency into a data dependency. Okay, just like we talked about abstractions of random I/O versus sequential I/O, a control dependency and a data dependency are two different ways of perhaps doing the same thing. And it turns out that data dependencies are actually much more efficient on modern processors than control dependencies. And the reason for this is that modern processors have out-of-order execution units, and so they can hold up the expressions that haven't quite got their operands calculated yet, and in the meantime do other operations in parallel. Whereas a control dependency, you don't really know what the next instructions really should be, and so there isn't a clear statement of parallel work you could do that's always guaranteed to be useful. If you predict wrong, that will be unuseful work and you will have to undo it. So this idea has had some influence. It's been used by some others, for example, to speed up quicksort. You can imagine how quicksort works, moving through the data from the right and the left, and the conventional implementation of quicksort will do if tests all along. It turns out it's even faster if you replace the testing with a data-dependent version rather than a control-dependent version. Let me now move to another topic. How do you size a hash table? Well, it's very easy to handle a hash table whose size is a power of 2. You can compute a hash function and use, let's say, all of the bits of the hash function. Maybe you drop some number of bits to get a number of bits that corresponds to the size of the hash table, and it's not a difficult computation to do. On the other hand, having a hash table that's required to be a power of 2 could be wasteful. Maybe you're wasting space by having a hash table that's too big, or you're wasting time by having a hash table that's too small and therefore has too many overflow buckets or collisions or whatever. Maybe you really want some kind of intermediate size. So the conventional solution to this is to write an expression such as the slot is equal to the hash of a key, which is some number in the range of 0 up to some power of 2 minus 1, mod size, okay, where size is how many entries you want in the hash table. So this will map a hash function into a range from 0 up to size minus 1. So that's mathematically fine, but it's something that we're going to do over and over again in the inner loop of all our hash operations. And it turns out integer division is very slow on modern processors, surprisingly slow. So what can we do about this? Well, the first step is to perhaps realize that there's something worth optimizing here. Let's abstract this and think of this as a function now, a key to slot function. And we're thinking even though it's a very simple function, just one line of code, it's probably worth optimizing because it's in the inner loop and going to be called over and over again. So here's the solution. So we know that integer multiplication, even 64-bit integer multiplication, is fast. And we also know division by powers of 2 is fast. You just do a few shift operations. So can we do something that doesn't involve integer division, yet still uniformly distributes the hash values across the slots in the range of 0 to size -1? Well, what you can do is think of a hash value as some 32-bit fractional number. And think of size as a 32-bit integer. Now, if you multiply a binary fraction by a 32-bit number, you will get a number that is some fraction of that size. Okay, and so we will basically uniformly split the range of 0 up to size -1 into a number of ranges that will be mapped by our hash function. So we multiply these 32-bit numbers and we get a 64-bit result. You can think of the high order 32 bits of that as the integer part and the low order 32 bits as the fractional part of that product. You just shift right 32 bits or divide by 2 to the 32, and now you have a value for your hash that is a slot between 0 and size -1. So this is an idea I proposed in 2006, 2007. It was subsequently noticed and promoted by Lemire in 2016 on his blog, and it has been adopted in several deployments, including Google TensorFlow. So this is curious that it's just one line of code, but yet it can have such an impact, perhaps a disproportionate impact. So abstractions are not just for large collections of code. You can really gain something from focusing even on single lines of code and improving their performance. I'm now going to talk about adaptive aggregation. So I talked about the idea that you have many cores working in parallel on a modern CPU, and you want them to cooperate to do a task that much more efficiently. So here's a fairly simple database task to do a grouped aggregation. So select G, sum of B, from R, group by G. G is our grouping variable, and we want to add up the B values for each of the G's. So there are a couple of standard solutions to this. You could have one really big hash table that all of your threads concurrently update in order to compute your overall aggregate. In order to do this safely, you have to manage the concurrent access. So some threads might access common items, and you want to make sure they don't interfere with each other. So you can do this either with locking or with atomic operations. So operations like sum, there are operators in some architectures that guarantee that you can do an atomic sum operation, slightly more time-consuming than an ordinary sum operation, but you can be confident that your result will, in fact, not suffer from interference. So this is okay, but it can provide performance problems. For example, if there's a few frequent G values, then all of your threads will be queuing up waiting for this G value that will basically cause you to serialize and not have much parallel execution going on at all. An alternative solution would be to use many independent hash tables and combine those hash tables at the end. This has very high space overhead. If you have to store a hash table a size proportional to the grouping cardinality on every thread, you've just multiplied your space budget by the number of threads, which could be very high. And you exhaust your cache memory more quickly, so you'll get more cache misses and so on. So neither of these solutions is entirely ideal. So in 2007, we introduced a new abstraction, which is a kind of hybrid table. You have a local table in each thread that will do some aggregation in cache. And in fact, you choose the size of these local tables so that in aggregate, they add up to less than the appropriate cache capacity. And when you spill out of these local tables, you update a global table. What that means is that if there are any very common values, all the threads will be updating a local table with those values. Those local values will stay in the local table because they're accessed frequently. And we don't need to do locking on the local tables because each thread has exclusive access to their local tables. Only when data spills out of these local tables, when some item that hasn't been updated in a while needs to make way for a new item that just gets added, that gets spilled to the global table. And so that is done with locking, but hopefully that represents the accumulation of multiple local aggregations, particularly for common items. So this idea of a hybrid table has been used also by others, such as DB2Blue. This isn't a universal solution. It's not always best to use a hybrid table, but you can choose an algorithm based on dynamically sampling the statistics and using a hybrid table like this. If there is locality in the data references, in the G values, or contention, and if you don't see either of those, then perhaps just go for the global table because then you won't have the contention problem anyway. I'm now going to switch gears and talk a little bit about hardware rather than software. So if you're designing hardware to do a data-intensive query processing workload, what would that look like? That's the question we asked in the Q100 project. This is joint work with my colleagues, Martha Kim and Stephen Edwards at Columbia, together with several graduate students. I should mention I'm going to acknowledge all of these graduate students that worked on these projects at the end, so stay tuned for that. The diagram at the bottom left here shows an SQL query and its translation into a flow in the Q100 system. The little boxes here, the nodes, are operators that the Q100 implements, and they are connected via an interconnect so that the data flowing out of one operator can flow into the input of another. By the end of this flow, we'll have the query result coming out here. We may need more operators than we have available in any one particular Q100 instantiation. A particular instantiation of the Q100 will have a fixed budget of operators. And so what you see here on the right is a situation where, because we have a fixed budget of operators, we need to execute the query in stages. Intermediate results are written to the RAM, and by the end of the third stage, we will have fully executed the query. We carried the Q100 design through the physical design stage, measuring the area and the power, and then we did cycle-accurate simulations in order to measure the runtime. I should also mention that in subsequent work, Baidu implemented an FPGA version of the Q100 design. So here are some results on TPCH scale factor 1, normalized to the time that one thread of MonADB would take as of 2014. And you can see on the left, where we show the runtime, that the performance is pretty good compared to single-threaded software. If you imagine an ideal multi-threaded implementation on a conventional CPU that provided 10 threads, the performance might be roughly the same. So it's comparable performance, say, to a 10-threaded CPU running an idealized parallel software system. Note that there are 3 designs here for the Q100 system, one designed specifically for low power, one designed specifically for high performance, and one sort of in between that is sort of Pareto optimal in the intermediate range. On the right, we see the energy consumption of the accelerator. And here, the improvement is much more dramatic compared to software. It's a factor of 100 compared to the single-threaded software implementation of MonadDB. So this conclusion suggests that you might want to put in a database accelerator not necessarily to speed up your queries, but just to make them much less energy consuming. And so an accelerator might be a good use of transistor space in order to make common query operations more energy efficient in a large-scale system. In follow-up work, we looked at a slightly different way of abstracting this problem. So having done the Q100 design, we observed that there are some potential inefficiencies in that design. First of all, the tiles could be idle. If we map a query to the tiles that we have on the accelerator, we may not use all the tiles. So some of the tiles may just be sitting there not doing anything. A second problem might be some kind of over-provisioned operator. We may have a column stitcher that's designed to stitch 4 columns together, but we only actually have 3 columns in this particular query, so not all of the circuitry is going to useful work. We may end up with interconnect congestion. So even though the operators are all moderately occupied, because certain links between them are saturated more than others, we might find that the downstream operators, which perhaps get only filtered data, are not being utilized as much as the upstream operators, and so we get underutilization there. And we can also have load imbalances as different parts of the circuitry see data distributions that mean that not all of them are getting their full complement of work. So the alternative design is to abstract things differently. Instead of having all of these specialized units, instead have some more general units that are organized, say, in a mesh, like in the diagram on the top. This is a homogeneous mesh of processing elements that have small instruction sets that allow them to be used as components of all of the pieces that we talked about earlier in the Q100 operator set. And so an operator can be mapped to a collection of these elements, not necessarily a single element, but a collection of these elements. And so here in the diagram below, you can see that certain operators may map to groups of nearby processing elements, and by mapping those elements to parts of this mesh on the chip, we can organize the data flow in such a way that the data flows through these operators in this general purpose way. So because it's general purpose, the operators may not be as fast as the specialized operators that do one specific thing. And we can see here in the top diagram that there are, in fact, overheads for each of these operators relative to Q100. The overheads are not insignificant for doing it this way. However, because of these inefficiencies that we talked about earlier, you can more than make up for the overheads by more efficiently utilizing the resources you have on the chip for the query you have at hand. So you get much more flexibility in deciding how to map your particular query when you have these general purpose nodes that are somewhat interchangeable, rather than having a bunch of fixed function nodes that are allocated in advance. And so when you look at a bunch of candidate designs, like we have in the bottom diagram here, comparing the Q100 designs, which are these green dots, and the homogeneous designs, which are the blue dots, the left diagram shows that you can have designs that perform well even with very small area. And on the right, you can have designs that perform well even with very small power. So if you're looking for a design that is particularly small or particularly energy efficient, then this master of none style of execution is probably superior to the Q100 style approach. I'm now going to talk about VIP, a partition-centric database management system. So conventional joins in databases often have a build then probe structure. And if you do a build then probe without partitioning, you're going to get lots of cache misses if your build table is big. And you'll also underutilize a lot of your single instruction multiple data parallel operations, because they don't work nearly as well for operations like scatter and gather when the data is not cache resident. So what's an alternative way that you might build a system? On a machine like the Xeon Phi, we have high bandwidth memory, which is particularly efficient and allows us to read and write much faster than we could to conventional RAM. The impact is that partitioning now becomes very fast, and it's now feasible to do all of this extra initial work to partition the data in order to get cache-sized pieces that are very, very efficient to operate on using SIMD instructions in that manner. So the chart at the bottom shows essentially that high bandwidth memory gives you very fast partitioning. So the numbers at the bottom, 4, 5, 6, 7, 8, that's 2 to the 4 up to 2 to the 8 partitions. And the solid lines are the high bandwidth memory. The dashed lines are the conventional memory. So you see a very significant improvement in the partitioning performance when the data is in high bandwidth memory. So what does this mean for design of a database management system? At an abstract level, if you have access to one or two hardware features like high bandwidth memory and very efficient SIMD, that totally changes your thinking about how you might organize your database management system. In fact, you might change your high-level design in such a way that it is partition-based, that the whole collection of operators are focused on partitioning down to cache-sized pieces, then processing those cache-sized pieces. So a totally different design might result. I'd now like to switch gears and talk a little bit about adaptive code generation. So there are many features of a query that are hard to predict or hard to know in advance. The data could be ordered. There could be hardware details. This is true not just about database queries, but it could also be true of code that you write in a procedural programming language. VectorWise in 2013 made an important insight, and they observed that there were variations of this kind which they had trouble predicting. And so what they did was to compile many versions of different database operators and have a repertoire of different compiled versions. They would then run those operators on chunks of the data at a time, measure the actual performance cost, and effectively learn which plan happens to work well on the data currently being seen and on the hardware currently being used, and to selectively exploit the best operator for the current data. So instead of optimizing based on predicted future performance using a cost model, they were using actual performance using performance measurements. In a project that we are looking at now at Columbia, we're trying to generalize this to arbitrary programming languages. Rather than just optimizing a handful of database operators, can we take an arbitrary compiler for a programming language, such as the Truffle-Graal compiler, and have the same kinds of built-in optimizations? If you have a loop, like the selection loop we talked about earlier, can the compiler automatically figure out which variant of the algorithm works best? And so we see, in practice, you have performance diversity. The two examples I've shown here are SIMD versus scalar, where sometimes skew makes SIMD bad because many SIMD lanes are trying to write the same data item. But in the absence of skew, SIMD is actually more efficient than scalar. On the right, we see that different versions of the selection function that we talked about earlier in the talk have different regions of optimality depending on the selectivity. And we may not know the exact selectivity, and the selectivity itself may vary within the data set depending on the conditions, particularly if the data has an ordering property, like ordering by time. So in order to get this to work at scale, the compiler is a key technology. If we have n algorithms that we need to implement and m target platforms, then considering every possible combination is mn implementations. That's obviously not going to scale. So one style of solution is a library, where you build a set of well-defined functions, such as linear algebra functions, implement your task using those APIs, and then every platform has an implementation that is efficient for that particular processor, and so your code can run on many machines and still be efficient. This works quite well for limited scope tasks like linear algebra. Compilers should be the enabling technology for this, and in fact, they have been a solid technology for using arbitrary high-level code on many processors. You write your task in a high-level language, and then every platform implements its own back end so that it can be used by a compiler. And so, again, you have an n plus m style solution rather than m times m. Nevertheless, being able to most efficiently use the processor is a big challenge for compilers, particularly since we don't have limited scope like a linear algebra computation. We have arbitrary code. So some compilers do a little bit of adaptive computation. They, for example, detect when pieces of interpreted code are being used a lot, and they dynamically decide that this is a hotspot, and they want to compile on the fly and then start running the code in compiled mode. So what our project at Columbia is trying to do is take this a step further and make the runtime execution of this data-intensive code blocks resemble this adaptive query processing we talked about earlier, where you have multiple compiled plans, each tried in turn on chunks of the data, and then you go with the plan that's working best on your actual data. So how might we make life easier for the compiler if this is such a challenging problem? I propose that we should expose declarativeness. This is something that the database community has been looking at for a long time. One of the advantages that we teach our students in our introductory database classes is how important declarativeness is. It allows the system under the hood to make a whole lot of implementation decisions that your average query writer may not appreciate. So perhaps we can augment our programming languages with declarative features to replace procedural constructs. So for example, the double ampersand and single ampersand, maybe we can replace that with an SQL-like and we can replace loops with a variant of a where clause. This would allow the compiler to reason at a higher level. So it's not always the case the P double ampersand Q is equivalent to Q double ampersand P. The compiler has to do a fair bit of work to figure out that there are no side effects and that those are in fact equivalent expressions. Rather than force the compiler to do that work, if we know that that is in fact true, let's write it directly and communicate that information to the compiler. So at the bottom, I've shown a particular way that you might implement matrix multiplication using a more declarative formulation with wheres and ands rather than using the standard nested 3 for loops. At this point, I'd like to acknowledge Jeff Ullman and Al Hayhoe for receiving the recent ACM Turing Award for their work on compilers. The work they did, they literally wrote the book on compilers, is very influential. It's something we're almost taking for granted these days, the very effectiveness of compilers at taking arbitrary code and generating machine executable code on a variety of platforms. It's almost so ubiquitous that you don't quite realize how influential it has been. The first reason this photograph is important is because it proves that long ago I did actually have quite a lot of hair. The second reason this is important is that Jeff Ullman was my PhD advisor and was also a very prominent member of the database community himself. So in a sense, this has completed the cycle in the timeline that I've been proposing. We've gone all the way back to 1991, and we are tying up some of the contributions in databases and compilers and perhaps setting the ground for some more progress in the area. So to summarize, I promised that I'd fill in some of these boxes, and here we have the boxes filled in. We've looked at several abstraction levels. At the software level, we've looked at the language level for compilation. At the system level, we studied VIP and partitioning. At the operator level, we looked at cache-sensitive B+ trees, how to do selections, how to do aggregation. At the fragment level, we showed how to optimize even a single line of code for hash table sizing, which turns out to be quite important. At the hardware level, we talked about systems and operators and how to abstract those to get accelerators to do database work. So there are some acknowledgments I need to make. I've shown here the lead PhDs for each of the projects that I talked about today. I'll mention them: John Rao, John Czeslavich, Lisa Wu Wills, Andrea Lotterini, Orestes Polychroniou, and Wang Dezhang. They did most of the hard work in building these systems and experimenting with them and so on. I'd also like to acknowledge my collaborators, Stephen Edwards, Martha Kim, Eric Sedlar, and Lucas Stadler, who contributed to the work described here. The various funding agencies, including NSF, IBM, Oracle, Microsoft, and the Packard Foundation. And finally, as promised, you can find the publications from my homepage and just look them up based on the year and the title to read further about these various contributions. So thanks for listening, and if you're here for the SIGMOD conference, I look forward to answering your questions.
Thank you, Ken. Thank you for the wonderful keynote. Everyone in the webinar mode, as attendees, you can type your questions in the Q&A box, and then we can take them over to Ken. So while that might be happening, I can kick this off with one of my questions. So Ken, I wonder, some of these abstractions and optimizations, they obviously depend on hardware and utilizing hardware properties to make things faster. I wonder how you've seen those abstractions hold over time, over the last, say, 2 decades, and if you see hardware trends, changes, breaking these abstractions in the future.
Okay, thanks, Stratos. That's a good question. I think there are several places where abstractions have really held up quite well. One is the notion of memory locality at various different levels of the memory hierarchy. No matter how we've been changing hardware over time, locality has always been important in order to get good performance. Contention has always been an issue, and so resolving contention has been a priority both in OLTP and OLAP style applications. The nature of who's contending and so on may have changed, but that as a more abstract concept is something that occurs over and over again. The notion of SIMD, I think, has been getting more and more important. People have been extending the width of their SIMD registers in conventional CPUs. And you can think in GPUs of some of the processing that goes on there as being a situation where you're also getting vector processing of a kind. And so having a vector mentality when you think of algorithms, I think that's something that has been consistent over time. You asked about breaking abstractions. I have one example of that. On certain processors, when you use SIMD instructions at their full capacity on all the cores, what happens is that the chip heats up too much and the chip senses that and clocks down the frequency, right? So you think to yourself, I've worked so hard to break my code down into these parallel tasks, and I've got this one module that I want to make really fast, and so I vectorize it and use all the latest instructions, and I run it, and as a result, it clocks down my frequency by 20% or whatever it is, which makes not only that module slower than I thought it would be, but also the computation after that is slowed down, right? Because it's not an instantaneous change. So you've got this non-local change that's happened as a result. So that's a kind of frustration that you might have, where you like to think that you're in this abstract, self-contained world, but the realities sometimes get in the way, and you have to face those imperfections in your abstractions. Did I answer your question?
Yep, I have more, but I'll give it up to Divesh.
Okay.
Thank you.
So I want to ask sort of the opposite question, right? Which is, you've been building abstractions, looking at hardware capabilities and so on. Have you thought about abstractions that you would like hardware systems to implement that they don't currently implement?
So we've thought about that, particularly in the context of the Q100 work and the Master of None, where we've kind of had the opportunity to build in whatever we felt like at the time. We thought a little about what we could implement. We had some fundamental choices to make. For example, we could have done things by partitioning, or we could have done things by merging, sort of a bottom-up or a top-down style of design. And for the Q100, we ended up choosing the top-down, the partitioning approach. So we kind of committed to that one style, but I don't think that was the only choice. I think that there are many alternatives. So there's no kind of easy answer to that, because there are all these different trade-offs. If you have one particular feature, it could be complementary with another feature, but conflicting with that other feature. And so it's really a menu that you have to put together as a whole, rather than thinking about the features one by one. That being said, our work on the Xeon Phi machine has told us that high bandwidth memory is really helpful for doing this partitioning work. And we were disappointed to hear that the Xeon Phi is being discontinued. I guess the good news is that there are other processors like the recent ARM processors that also have high bandwidth memory. And so, you know, if you were to ask me what might be one thing that current processors don't have that they perhaps should have, I think it would be high bandwidth memory for facilitating this sort of fast partitioning and things like that.
Thank you, Ken. So Strata, if I can ask a follow-up question.
Sure.
So you mentioned something quite intriguing, Ken, that you find that there are abstractions that are not always compatible, right? You have one abstraction and you sort of break another one. Have you thought about, and maybe you already have you been thinking about sort of a theory about how these abstractions, which ones work together, which ones don't, and why?
I don't think I've thought about it in a systematic way along the lines that perhaps you're hoping for. I think in specific instances, there are certain decisions you make that preclude other subsequent decisions, and you kind of face those one at a time as you're trying to solve a particular data management problem. I mean, I could list a lot of very specific examples, but I think that's not what you're looking for. I don't have a sort of overarching theme about how to marry certain features with other features and know that they'll be good together. I think there are empirical ways that you could do that. You could just throw things together and see if they're compatible or not. If you have a cloud platform and you want to have multiple tenants and you're not sure whether their workloads work well together, well, you just throw them on and see, do they conflict with each other or do they work in harmony? And you can get empirical results like that. But a more theoretical or principled approach, I'm not sure I have any answers for you.
Thanks, Ken.
So there is a question by Manos Athanasoulis on the Q&A, and Manos asks if you can see more relational operators being developed in hardware in the future, and how this whole discussion changes with cloud-based systems, and in general, if it is possible to effectively keep pushing down operations, computation, I guess in other hardware levels.
Yes, so cloud-based systems offer an opportunity. I heard an interesting statement in one of the Damon talks earlier today that I agree with, and that is it's easier to sell a new approach on the cloud than it is to try to convince people to buy a brand new machine. If all they have to do is rent the machine rather than buy it, and you put the platforms up there, they can try it out and see if it works. So I think, and apologies to the person who I'm quoting here without remembering their name. I think that the cloud provides an opportunity here for ambitious sort of vendors who want to take the next step in trying to build architectures that attune to a particular kind of workload. All of the technologies that I've talked about and several others, persistent memory and so on, are very active right now in terms of how they might help performance. Performance per watt, performance per dollar are now far more interesting metrics in the cloud than just response time and so on, which are the traditional metrics we used to measure ourselves by.
Thank you, Ken. I would like to pass it on to Goliang in case there are questions from the audience on site.
Thanks, Ken, for the very nice talk. So I have a question. So, AI drive the hardware to design new hardware for AI, for example, AI chips. So my question is that besides we utilize the modern hardware, can we design the new hardware for database, for example, data management and data science? Can we have DB chips, data science chips, and data management chips? And if yes, how can we design if we know why? Thank you.
Okay, so the idea of a DB chip, I think is not a bad one. I don't think it will necessarily be a standalone chip. It might be one chip, one piece of a much bigger chip that does data management, just like you have a particular video rendering accelerator or a floating point accelerator on a chip. You may have a certain part of the transistor budget devoted to data processing chips. In the architecture community, accelerators are now mainstream. People there are looking in many different domains for domain-specific acceleration of various kinds. AI is just the most obvious one because of its high demand. But I think that there are many situations where this is going to be useful. So I don't have any predictions that a vendor is about to develop a database chip that is going to revolutionize data processing in the sense that you're looking for. But I think gradually we're going to get there as more and more domain-specific accelerators are out there and get utilized and accepted by the broader community.
Thank you.
Okay, there's one more question on the chat, but we'll actually do it tomorrow because we do have to close now. Ken, thank you so much for this wonderful keynote, and thanks everybody in the audience. We will be able to take more questions with Ken in the repeat session tomorrow morning or night, wherever you are, depending on the time zone. Thank you so much, Ken.
Thank you, Stratos.